In this video, we will look at using variation of parameters on higher-order non-homogeneous differential equations. If we recall from second-order differential equations, the big advantage of variation of parameters is theoretically it could be used to solve any second-order, or in this case, any higher-order non-homogeneous differential equation. That's different from the last method we looked at, which was undetermined coefficients, which was only useful for g of t of certain forms, polynomials, exponents, sines, and cosines. For variation of parameters, theoretically, it can be used for any differential equation. However, realistically, the first step is to find the general solution of the corresponding homogeneous equation, and we noted for second-order differential equations, and it's also true for higher order, so far we have only shown how to solve the homogeneous equation if and only if it has constant coefficients. Nevertheless, there are many differential equations, and you can see that come up in applications that are just this way, homogeneous. When you look at the homogeneous, there's only constant coefficients. So it's not as big as a drawback as it might seem at first. Here is the form of the differential equation we will be solving. Again, we have an nth order, linear, non-homogeneous differential equation. The first step is to find the general solution of the corresponding homogeneous equation, and here we've written out the complementary solution is going to be of this form, c1 y1 of t plus c2 y2 of t up to cn yn of t. So far, we have only shown how to solve the homogeneous equation only if it has constant coefficients. To continue, our next step is to take this complementary solution and replace the constants by functions u1, ut up to un, and we will get an equation of this form: y is equal to u1 times y1 plus u2 y2 up to un yn. Next, we choose n minus 1 additional conditions on the solution. And much as we did for second-order differential equation, we choose conditions that'll help simplify our calculations as we go forward. And we start by wanting to suppress the terms that lead to higher-order derivatives. So if you recall, for our second-order differential equation, we had these two terms, the terms that involve the derivative of u1 and the derivative of u2, and we set their sum equal to 0. So for our higher order, our nth order differential equation, we set the terms u1, u2 up to un prime, those derivative terms, summed together equals 0. Then we also take the second derivative of u1, u2 up to un. When they are summed together, that'll equal 0. And we do this up to n minus 2. With these initial conditions, you'll see that the nth derivative of y simplifies to this form, which involves no derivatives, u1 y1 to the m plus u2 y2 to the m up to un yn to the m. The next step then is to plug in all our derivatives, the derivative of y, second derivative up to the nth derivative, into our differential equation. That was the differential equation we're trying to solve, and set it equal to g of t. This part, the left-hand side, you will see once you've done all the simplifications and combine all like terms and everything, you'll see that you will get an expression that involves the first derivative of u1, u2 up to un, and no other terms. There's no terms with just u1, u2, or un. And now we can solve the system of equations. We have the n minus 1 equations from step 3. Those were our additional conditions, as well as the equation from step 4, which is important, the one we used when we plugged everything into our differential equation. This system of equations will have a solution if the Wronskian is not 0. Once we have this set of equations for um prime, we integrate with respect to t to find and this is the formula that falls out. For second-order differential equations, we solved two different examples, both by following these steps for this procedure, as well as just plugging into the formula. For higher order derivatives, we're simply going to use the formula. And also just a note, I do have Abel's identity here, which allowed us to calculate the Wronskian without actually solving y of c, written here for your reference. Here I have moved the formula and Abel's identity for your reference. And our first example is given y1 of t is equal to e to the t, y2 of t is equal to t e to the t, and y3 of t is equal to e to the minus t are solutions to the homogeneous corresponding equation, the third derivative of y minus y double prime minus y prime plus y equals g of t. We want to determine a particular solution of the non-homogeneous equation in terms of an integral. First, we will need to calculate the Wronskian. So here is my calculation of the Wronskian. We're given that y1 is e to the t, y2 is t e to the t, and y3 is e to the minus t. So here I have e to the t, its first derivative, and its second derivative. Here I have t plus e to the t times its first derivative and its second derivative. And then last I have e to the minus t and then its first derivative and its second derivative. So I'm going to go ahead and pull out my e to the t just to make things a little easier, because this is sort of a constant. And then when I pull that out, I have 1 in the leftmost column, and then I have my t plus 1, t plus 2 in the middle column, my 1 minus 1, and 1 in the far right column. If you don't pull out the e to the t, that's fine. I just did this to make it easier on myself. And now we need to take a determinant of this 3 by 3 matrix, which we haven't done before. And what we do is we are going to consider the elements of the first row. And each of those elements are going to become the multipliers of, since this is a 3 by 3, of the next smaller determinant, which will be 2 by 2. So here, my 1 is the multiplier of my next 2 by 2. The t is the multiplier of my next 2 by 2, and we alternate signs. So this is going to be a plus 1, this is minus the second element, and then this last one here is going to be a 1 times the last 2 by 2. So now the question is, how do I figure out what the 2 by 2s are? So when I'm looking at this first row, first column element, which is 1, I eliminate this first row and first column, and what I'm left with is the 2 by 2 that we're going to take the determinant of. Next, I'm going to take the next element, which is t, and remember we're going to alternate signs, so now this is going to be a minus t, and then I'm going to delete, since t is in the first row, second column, we're going to delete the rest of the first row, delete the second column, and what's left, this 1, negative 1, 1, 1, will be my 2 by 2 determinant. Finally, I'm going to consider the last element in the first row, and that's 1, and I'm going to multiply by the 2 by 2 determinant that we get by crossing out the first row and the last column. Again, because this element here, the 1, was in the first row, last column. So here's the 2 by 2 that we're left with, 1, t plus 1, 1, t plus 2. And now we know how to get the determinant of a 2 by 2, which is just kind of to cross multiply. And when we cross multiply in this direction, we add the negative sign. So we're going to have e to the t times t plus 1 times 1, which is t plus 1, minus, and this negative 1, so that becomes positive, 1 times t plus 2. Then we have our minus t, our 1 times 1, which is 1, minus negative 1 times 1, which is then gives us a positive 1, plus 1 times t plus 2 minus t plus 1 times 1, which is minus t minus 1. And what you see is we end up with 4e to the t for our Wronskian. I have made note of my Wronskian here is equal to 4e to the t. Now I'm going to look at my formula for y, my particular solution of the non-homogeneous equation, and I see it has a summation formula. So I'm just going to plug in y, my m equals 1 to 3 in this formula, and I get y1 of t times the integral gs w1 of s over my Wronskian, plus y2 of t, my g integral of gs w2 over my Wronskian plus y3 of t times the integral gs w3 of s over my Wronskian. So I need to calculate these w1, w2, and w3. And here is the definition of what these wm are. They're the determinant obtained from w by replacing the mth column by the column 0, 0, 0, and then the last element is 1. And this is transpose, so it's just the regular kind of column vector you're expecting. I'll start by calculating W1, and again, that's the Wronskian matrix or determinant, but I replace my first, because we're at W1, so I'm going to replace my first column by the column with zeros except for 1 in the last element. So here it is. My first column has zeros except for the last element. My next column is the same as the normal Wronskian. It's going to be t e to the t, its first derivative and its second derivative. And the last column will be e to the minus t, its first derivative and its second derivative. I'll start calculating the determinant of my 3 by 3, and I start by looking at my first row. So the first row, first column, the element is a 0, so I don't really need to worry about the rest of the 2 by 2 determinant since it's going to be multiplied by 0, but this is what it would have been. Next, I'm going to look at my first row, second column, and I'm going to alternate my signs, so it's a negative t e to the minus t, and then the 2 by 2 determinant that comes with that will be the 0, the e minus e to the minus t, my 1, and my e to the t. Finally, I have my first row, last column, and the determinant that is associated with that, the 2 by 2, is 0, t plus 1 e to the t, 1 t plus 2 e to the t here. And then I calculate my determinant, and I see it's equal to, for W1, is equal to minus 2t minus 1. And I'm going to make note that W1 is equal to minus 2t minus 1 up here. Next, I calculate W2. Again, I take the second row, because now it's 2, W2. Take the second row, replace it with 0, 0, 1. I have my e to the t, its first derivative, its second derivative, and my e to the minus t, its first derivative, its second derivative, and here I calculate the W2 is equal to 2. Last, I do this for W3. My last row now, or my third row, is 0, 0, 1. I have e to the t, first derivative, second derivative, my t e to the t, first derivative, second derivative, and my Wronskian ends up being, my W3 equals 2 e to the t. And I make note of W1 and W3 over here. Now that I have all my components, I can plug into my formula. I'm using s as my variable of integration. So my g of s is equal to e to the s here, and my Wronskian on the bottom is 4e to the t. So I have y1, which is e to the t, times the integral e to the s. My w1 is equal to minus 2s minus 1 all over 4 e to the s ds. My y2 is t e to the t times the integral from e to the s. My w2 is 2, and then my Wronskian is 4 e to the s on the bottom. And finally, I have y3, which is e to the minus t, the integral e to the minus s. My w3 is 2 e to the s all over the Wronskian 4 e to the s. And it asks for this in terms of an integral, so this is where I can leave my answer. My next example is to find a solution to the initial value problem y triple prime minus y prime equals tangent of t, and I also have y pi over 4 equals 2, y prime pi over 4 equals 1, and y double prime pi over 4 is equal to negative 1. I start by solving my homogeneous equation, and my characteristic equation is r to the third minus r, and factoring, that will give me r times r squared minus 1, which is equal to r minus 1, r plus 1. So our general solution for the homogeneous equation will be c e to the 0, or c1, plus c2 e to the t, plus c3 e to the minus t. The next thing I want to do is solve for the Wronskian. Here I have 1, and its first derivative is 0, its next derivative is 0. Now I have e to the t, its first derivative and second derivative are also e to the t, and finally I have e to the minus t. Its first derivative is minus e to the minus t, and its second derivative is e to the t. I have, looking at my first row, I have 1 times eliminating this row and this column, I'm left with this determinant here, this 2 by 2, e to the t, e to the t, and minus e to the minus t, e to the minus t. Next, I have minus this element here, which is e to the t, times the determinant, like I'm eliminating these two, so I'm left with 0, 0 here, and minus e to the t and e to the t for the final row. And then last, I have my e to the minus t. I'm eliminating this column and this row, and I'm left with 0, 0, and e to the t, e to the t. And when you calculate this out, you have that is equal to 2. And I will make a note that the Wronskian is equal to 2 right here. Next, I'll calculate W1. So I take the same Wronskian matrix, but I substitute the first row with 0, 0, 1. And I get W1 is equal to 2. And I make my note here. My W2, I take the same Wronskian, substitute the second row, though, with 0, 0, 1. And I get my W2 is equal to e to the minus t. And finally, W3, the third row is replaced with 0, 0, 1. And I get W3 is equal to e to the t. Now that I have all the components solved for, I can plug into my equation. When m is equal to 1, I get y1, which is just 1. Then g of s is tangent of s. W2, or W1, I'm sorry, is minus 2 over the Wronskian 2. Plus, now I plug in m equals 2. I have y2 is e to the t. The integral g of s is just tangent of s. And then my W2 is equal to e to the minus s over the Wronskian 2. Plus, now plugging in for 3, my y3 is e to the minus t, integral, g of s is tangent of s. My W3 is e to the t. Since my variable of integration is s, that becomes e to the s over the Wronskian 2. In this case, I'm actually asked to find a solution, not just to leave it in integral form. My t naught here is equal to pi over 4. So I'm going to start by plugging that in and doing some simplification. Here, my 2's cancel out. I pull out my negative, t over 4 to t, tangent of s, these again cancel out, ds. Plus, I'm going to pull out my 1 over 2, 1/2 e to the t, pi over 4 to t, tangent of s, e to the minus s ds. Again, pulling out the 1/2 e to the minus t, integral from pi over 4 to t, tangent of s, e to the s ds. I can't really do a lot with this e to the s tangent to the s right now, but I can simplify this tangent of s. So I integrate tangent of s, I get secant of s, and I can plug in my limits of integration t and pi over 4, and I'll get natural log of secant of t plus natural log of secant of pi over 4. So from here, I have natural log of secant of t plus natural log here of square root of 2 plus, and I have my 1/2 e to the t, pi to integral e to the s tangent of s, and my 1/2 e to the minus t integral of e to the s tangent of s. So finally, my general solution looks like C1, it's my homogeneous equation, C1 plus C2 e to the t plus C3 e to the minus 3 minus my natural log of secant of t plus natural log of square root of 2 plus 1/2 e to the t integral e to the s tangent of s plus 1/2 e to the minus t integral of e to the s tangent of s. So here's my general solution, but I still need to plug in my initial values to find my coefficients. Plugging in pi over 4 now for t into y, I will get that y pi over 4 is equal to c1 plus c2 e to the pi over 4 plus c3 e to the minus pi over 4. I'm just going to write the final conclusion for y pi over 4 over here now. Now I need to look at my second initial condition, which involves the first derivative of y. So looking at this, it looks kind of ugly, but then I realize, wait, if I have the integral of the derivative, this is going to be easy. Except then I realize, oh wait, I have this other function of t So I'm going to need the product rule. So it's not going to be quite as easy as I first initially thought, but it's not that terrible. So y prime of t, this goes away. I get my ct e to the t, my c3, my minus, because of this minus t, minus c3 e to the t. Here I have tangent of t. This goes away because it's a constant. And now, using the product rule, I have my derivative of 1/2 e to the t, which is just 1/2 e to the t, times my integral, plus my 1/2 e to the t times the derivative of the integral. So the derivative of the integral is just going to be my e to the minus s tangent of s evaluated at t and pi over 4. And that's what I have written here. Similarly, for this product, I'm going to have the derivative of 1/2 e to the minus t, which is just minus 1/2 e to the minus t times the integral, plus now my 1/2 e to the minus t times the derivative of the integral, which is just e to the s tangent of s evaluated at t and pi over 4. Now when we plug in pi over 4 into y prime, we have our c2e to the pi over 4 minus c3e pi over 4. Our tangent goes to 1, so we have minus 1. Here, this looks like it's going to be ugly, except for the fact that our integral now is from pi over 4 to pi over 4, so that will give us 0. Fortunate. Then we have our 1/2 e to the t pi over 4, but if you look at this here, when I plug in my pi over 4, my tangent, this becomes 1, and this t is pi over 4. So I have e to the minus pi over 4 minus e to the pi over 4, so this will become 0. So that can go away. Here I have my 1 minus 1. Similarly here, because the integral goes from pi over 4 to pi over 4, that becomes 0. And here, when I plug in tangent pi over 4, that's 1. And then I'm going to have e to the pi over 4 minus e to the pi over 4, which will give me 0. So I have my 1/2. So my y prime of pi over 4 simplifies to c1 plus c2e to the pi over 4 plus c3e to the minus pi over 4. And I am going to note that here. So y double prime looks ghastly. It's this much, and then I kind of started to combine terms. And then I plugged in pi over 4, and I get this ending expression, which I have noted here. Using my 3 equations now from my 3 initial conditions, I can solve for C1, C2, and C3, and this is what I get. C1 is equal to 4, C2 is equal to e to the minus pi over 4, and C3 is e to the pi over 4, which means my final solution is first the solution to my homogeneous equation. But I can plug in 4 for C1 plus, what is C2? E to the minus pi over 4 times e to the t, so that will be e to the t minus pi over 4, plus C3, which is e to the pi over 4 times e to the t, so I'll get e to the minus t minus pi over 4. And then I have my homogeneous solution, which is equal to my natural log of secant t plus natural log of 2 plus 1/2 e to the t with my integral e to the s tangent of s plus my 1/2 e to the minus t and my integral e to the s tangent of s ds. So this is my final solution. So to review what we've looked at, we looked at using variation of parameters on higher order non-homogeneous differential equations of this form here. The nth derivative of y plus p1 times the n minus 1 derivative of y up to p of n minus 1 times y prime plus p of n y equals g of t. We mentioned that the method, the steps we use for the variation of parameters, we can use totally analogous steps for the nth order differential equation. And what we can do then is come up with this equation for our solution. Unlike second order differential equations, once we have this equation, we only use this equation. Generally, it's you can, if you want, go through all these steps, but it's easier just to use this equation, which we did for 2 examples. So that's it for this video. Thank you for watching.